briefly, I want to talk about time. This is a presentation I tend to give to schools. So at the beginning, maybe it's going to be a little slow for the astronomers, but I think we'll pick up a little later. So what we're going to do first off is, what is a year? It takes the Earth 365.256 days to rotate fully around the sun, to revolve around the sun. And we call that a year. That's very easy and straightforward. So basically, there's the belief that it's warmer on Earth during the summer because the Earth is closer to the sun during the summer. That is not true. Many people tend to believe that. The Earth's orbit is an ellipse. It's not a perfect circle, but it doesn't cause the seasons. In fact, the Earth's close to the sun around January 3rd, furthest from the sun around July 4th. So it has nothing to do with the seasons. The seasons are a result of the tilt of the Earth's axis. It's 23 degrees, and it's basically the way it goes. And the number of daylight hours and the warmth is more for the half of the Earth that's pointing toward the sun than away from the sun. So winter starts on December 21st or 22nd, around that time, when the north is tilted furthest away from the sun. Then what just happened today was we went into spring, vernal equinox, 20th or 21st. That's when neither the north or the south is pointed toward the sun, but the equator is directly pointed at the sun. Summer solstice, 20th to 22nd, is when we're pointing furthest toward the sun. And then the autumn equinox, again, the equator is pointed at the sun. Just basically, this is the way the picture looks in most school books. Very confusing. And that's why kids get very confused on this topic. So, again, this statement I have a lot of fun with. Days get shorter in the winter and longer in the summer. That is not true. The shortest day of the year is the first day of winter. The longest day of the year is the first day of summer. So after the shortest day of the year, days start getting longer. After the longest day of the year, days start getting shorter. In winter and spring, every day is longer than the previous. In summer and fall, every day is shorter than the previous. So the days are getting shorter in the summer and longer in the winter. They are shorter in the winter, but they're getting longer. So a day. What we call a day is the interval between two successive transits of the meridian by the sun. Meridian being a center, the center line of the sky, halfway between sunrise and sunset. And we divide each day into 24 hours kind of arbitrarily. And the time before the sun crosses the meridian is called AM, ante-meridian in Latin. And after it crosses the meridian is called PM, post-meridian. So that's time. The names, I'm not going to go through all of these, except it's kind of interesting. September, October, November, December are all just counting in Latin, 7, 8, 9, 10. And again, the days of the week are named mostly after English or Germanic gods. So, time zones. Prior to the 19th century, everybody had their own time. Now, it was not a problem when the fastest possible transport was by horse. What happened is you would go into a town, look at the town clock, set your watch to the town clock, and then you'd be in time along with everybody else. that the times were set based upon when the sun crossed the meridian. So two close by towns could have different times. This became a problem when railroads were built. Two towns only a few miles apart would have different times. That wouldn't work with railroads. They needed schedules and they needed to share tracks, so they needed to have a common time. And at that time, railroad established a time, and it was different than local time. And there were actually watches with multiple extra hands on them in order to keep track of railroad time versus local time. And this is the kind of problem we had. Pennsylvania Railroad operates on Eastern War time, 1 hour faster than Ohio time. So they had to put notices up talking about their time compared to the local time. So the real solution was time zones. So standard time zones were existed in US and Canada by the railroads in 1883. It had started several years earlier in Britain. It wasn't the law in the United States, so a lot of cities did not decide they're going to do it. Even Detroit decided they were not going to go on to standard time. Then in 1918, the government made a system of standard time zones law. Some places in the world still don't have standard time zones, but the United States doesn't. And these are our time zones as they pass. And our worldwide time zones. Now, interestingly, see where the 0 is. Right down here. Time is measured relative to the time in Greenwich, England. It's called Greenwich Mean Time, Zulu Time, Universal Time, and a lot of other names. And Greenwich is a small suburb of London, but the Royal Observatory is in Greenwich. And that is the reason, that is the basis. And the time measurements by astronomical observations. Interestingly, and I don't have time to go into the whole thing, but there was in 1714, England passed a longitudinal act and established a prize of $20,000 for a method to determine the longitude within half a degree for a ship at sea. $20,000 then was over $1 million today, or 20,000 pounds is over $1 million today. It was a very big prize. No one person won it. A number of people took various parts of it. And the solution turned out to be a combination of an accurate clock that would keep time at sea and instruments to measure the angle of astronomical objects over the horizon, and a set of tables showing where these objects were when seen from the Royal Observatory in Greenwich, England. So therefore, the clocks the ships carried were set to Greenwich time. So they knew what time it was. That's how it became a standard time. The tables were relative to Greenwich. So those were the tables they had to use and the time they had to use. So that's how Greenwich got there. This is just a picture of the Royal Observatory clock. Now, why Greenwich? Now, the navigation, latitude is very easy to determine in the Northern Hemisphere. All you have to do is measure the height of the North Star over the horizon. That is your latitude, the number of degrees to the North Star over the horizon. In fact, instruments were designed for it, some as simple as a board with a string run through a hole in the center. that was used in ancient times to determine latitude. A quarter circle with degrees marked on it so you could read the height of the North Star. It's called a quadrant, 1/4. So when it was done, the Royal Observatory tested clocks and made all the necessary tables for finding your latitude. Okay, so again, if we look at time zones, we see 0. That is where Greenwich is, right here. So now there's another problem with our time zones. That is, if you travel west, you're traveling the same direction the sun appears to be traveling in the sky. By the time you go all the way around the world, you will have seen one less sunrise, sunset than people who didn't travel with you. That's what led to that great Jules Verne novel, Around the World in 80 Days. The guy going around the world counted 81. Well, he went the other way, but he counted 81 days, and actually 80 had only passed. So if it's 2:23 a.m. Thursday in Tonga, it's 3:23 a.m. Wednesday in Samoa, and they're 500 miles apart. The international date line's kind of quickly. You really don't want to have it go through any populated areas. That'd be very confusing. I think it's Tuesday and you think it's Wednesday. A 24-hour clock, going to cut this very briefly. Basically, you just don't stop counting at 12. You go on counting 13, 14, 15. And the convention is not to use the colon in the times. So 1 p.m. is 1300. 10:35 p.m. would be 22:35. Not 30 like my thing says. Daylight saving time. We just went through that. The idea was first suggested by Ben Franklin. His idea was to enjoy more sunlight and save the cost of oil. Sounded pretty good. It didn't go into effect to World War I, then to save electricity and help the war effort. And there were a lot of complaints. Farmers said it confused the hens. Well, confused the farmers. The hens didn't care. But the farmers had to get up early, or earlier than it said. Parents were worried about the kids and the safety when they're walking to school in the dark, and kids had trouble going to sleep in the light. They're having that trouble right now. Adults complained they couldn't sleep well, and most astronomers don't like it because they can't start observing until later at night. The reason we started our meeting late this week. So this is very complex, I don't really like too much, but after World War I, it was repealed. It was instituted for World War II, then repealed again. In 1966, it was set for the last Sunday of April and the last Sunday of October. Then it was established year-round again in 1966 because the energy crisis, under the legislation enacted in 1986, daylight saving time in the U.S. began at 2, the first Sunday of April, and ended 2 on the last Sunday of October. Then in 2007, we moved it to the second Sunday of March and the first Sunday in November. Keep coming in on both sides of it. The reason they don't implement it year-round basically is that people don't like having kids go to school in the dark. And on the western edge of the eastern edge of the time zones, that happens if daylight saving time's in effect. So here's the kind of problem you have. For those who can't see it clear, these are two guys looking at Stonehenge saying, remember, when daylight saving ends, we have to give everything a slight turn to the left. So, next fact is the Earth rotates on its axis once every 24 hours. That's not true either. It takes 23 hours and 56 minutes to rotate once on this axis. The additional 4 minutes a day are there because the Earth is also moving relative to the sun. So stars rise earlier, about 4 minutes earlier every day, about 30 minutes every week, about 2 hours every month, and exactly 24 hours earlier every year, or at exactly the same time at the end of the year. So, for instance, Betelgeuse rises at 21:53 on November 2nd, and that's where I am. And November 3rd at 21:49, December 2nd, 1955, almost 2 hours earlier. It was exactly 2 hours earlier. February 2nd at 17:53, almost 4 hours earlier. And November 2nd, 2021 at 21:53. So let's talk about really what time is. We tend to believe it's eternal, independent, universal, unique, and we experience past, present, and future. That's because that's what we needed to live and survive on Earth, those kind of beliefs. Time is not eternal. It has a beginning and will have an end. It began at the Big Bang. You can't ask what happened before the beginning of time or after the beginning of time, since beginning and end are time concepts. Somehow that hurts my head, but and relativity does indicate that time began at the Big Bang. So what happens before the Big Bang is a meaningless question. So time is eternal. Time is independent, constant, universal. Basically meaning independent, it doesn't matter where you are or how fast you're moving. Constant, everybody sees the same time. Universal, there's some great clock in the universe counting off time. Or unique, time is the same for everybody. However, we know, based on Einstein, that the stronger the gravity, the slower time passes. In fact, on the surface of the Earth, time passes 44 1,000ths of a second a year slower than it does in deep space. And that is a tiny change, but it has been measured. And the GPS system requires adjustment because, 1,000th of a second would take you almost 2/10 of a mile to a different place from where the GPS said you were. It would make GPS go off by 2/10 of a mile. And if you were to fall into a black hole, the universe would age and end as you cross the event horizon. Time would slow down that much for you relative to the rest of the universe. It also moves slower as you approach the speed of light relative to somebody who is not moving. Remember, everything is relative. You're to travel to another star and back at 87% the speed of light. Everyone on Earth would have aged twice as fast as you did. It's called the twin paradox. So, discussion about that. Oh, if you have a question, break in. Alice in the White Queen. I love Alice in Wonderland. This is through the looking glass. But with the White Queen, Alice says, I'm sure, talking about memory, I'm sure mine only works one way, Alice remarked. I can remember things before they happened. And the White Queen said, it's a poor sort of memory that only works backwards. So remember that. We got poor memory. And Einstein's comment is, but it was the distinction between the past, present, and future is only a stubbornly persistent illusion. So let's talk a little about time travel. I kind of like this, if you guys can see it. So, time travel. Man, I was going to post a time travel joke, but you guys didn't like it. Interested in time travel? Meet here last Thursday at 8 p.m. Now, time travel is possible into the future. We're all doing that right now. We can do it faster by going into higher gravity or by traveling at higher speed. But remember, all time is relative. Time passes us relatively slower than somebody at a higher gravitational field traveling at high speed. There is no such thing as correct time or the time. Time didn't travel necessarily slower for you. It only passed slower relative to what somebody else saw. So one thing is, if you could travel faster than light, you would travel back in time, if you believe relativity. And I love this little limerick. There was a young lady named Bright, whose speed was far faster than light. She set out one day in a relative way and returned on the previous night. So, of course, time travel is possible. I told you that next week. However, Stephen Hawking's comment on it was, if time travel is possible, where are the tourists from the future? Good question. Time travel to the past, going backwards, has some very serious problems. One of the most serious ones is the grandfather paradox. There's also duplication and a problem with your location. So I have not seen any questions yet. I think I've lost everybody, or I've put everybody to sleep. Okay. The grandfather paradox is simple. Suppose you absolutely hated your grandfather, went back in time and killed him. Well, this circle over here shows the process. You're born, create a time machine. You go into the past, you kill your grandfather. Therefore, your father is not born. Therefore, you're not born. Therefore, you didn't create a time machine and you didn't go into the past. So your grandfather's still alive. So your father was born. So you're born. So you create a time machine and we're in a loop. It's a logical paradox. You can't go back and kill your grandfather because if you do, you didn't do it. And if you didn't do it, you did do it. Another problem is duplication. In this cartoon, he's looking at the refrigerator, said, there it was, the same piece of cake he ate yesterday. His time machine really worked. Think of the possibilities. He could have his cake and eat it too. But if you stop and think about it, suppose you had a time machine that could put something back 10 minutes. You put a bar of gold in. Well, that bar of gold gets put back in 10 minutes. So it was already a bar of gold in the time machine 10 minutes ago. So now you got 2 bars of gold in your machine. You wait a little bit and the time machine activates again, sends it back 10 minutes. Now you got 4 bars of gold in your machine. You better stop that pretty quickly. You're going to be flooded with gold. But where did it come from? Where did the material to make that gold come from? The energy to make that gold come from? But putting that back in time obviously duplicates things. If you go back in time, well, you're still to a time when you were alive. There's 2 of you. Where'd that second one come from? So that's another problem with traveling to the past. And there's finally the one of position. Remember, the surface of the Earth, we are moving at about 1,000 miles an hour, about the speed of a bullet out of a high-speed rifle, eastward, just from the spin of the Earth. The Earth is moving at about 67,000 miles around an hour around the sun. So if I go back 1 hour in time, the Earth will move 67,000 miles. Am I still going to be standing there in outer space where I was? And of course, the sun's going around the sun at about 500,000 miles an hour. And we're traveling toward Andromeda galaxy, the whole galaxy, at about 250,000 miles an hour. So where are you going to wind up if you go back in time? So basically, summarize what all this says is into the future, time travel into the future is possible. You can even do it at a faster speed relative than the Earth. Time travel into the past is not possible, at least not in any way we can think about it. So anyway, that's what I have to talk about in time. And didn't take quite as long as I thought. Now, if we have any questions, what I'll do is I'll clear the screen. So I do kind of like